Let's get started. So here's what you were given. So here's this journey we're on. You know how fast something is changing at every moment? You want to know how much of it you have at every moment. So you know how fast something is changing at every moment. What is that in this on this quiz and what I'm showing? You know how fast something is changing at every moment. What is that? Well, specifically, what is it? R or R sub B? R sub B, the exact rate of change function. That's where it begins. That's the exact rate of change function for this plane launching out the window of a building. Okay, so we know how fast something's changing at every moment. That's R sub B. And so, what is the purpose of R? What is the purpose of R? If we have R sub B, why do we make another rate function? We already have the real rate function. Why do we make a rate function that's not even accurate? Okay, so the rate function that we make has constant rates of change. Why do we want that? What's that? Yeah, because then we've got the math to bridge to accumulation, to amount of change and then total amount. Okay, with a continually changing rate, we have no way to get to amount of change. With constant rate of change, we know the amount of change is just R, whatever the rate is, the constant rate, times the change in X. Okay, so to start building an accumulated height or height above the ground, so we can work with R instead of R sub B. So we have this for 2 seconds. It says the rate is what? -7. So for 2 seconds at a rate of -7, what's the change in height? Changes in height are just -7 times the change in time. So a change in height in the first 2 seconds of -14. -14. Meaning a decrease in height. So that gives us the point. What? 2, -14. Okay. Okay, so don't start talking every time. I know it's tempting. But just try to not talk. What? I'm sorry? Accumulated heights. This is the accumulated changes in height. But you're only 50 off. Right? But no, seriously, it's just he's only a constant off. If you did everything else right, then you're just that sum number off, right? But so just know that that's the difference between an amount and an accumulated amount. Okay? All right, so what about in the next 2 seconds? Our rate of change is -3. So if the rate of change is -3, given any change in time, the change in height is -3 times the change in time. So our next change in height is -6. And then the new accumulated height is the old accumulated height plus the change in height. So we're at -20. All right, what about in the next 2 seconds? +9. So 18, so then what? The new accumulated amount of height is the old accumulated amount of height plus the change in height, which the new change in height would be 2 times 9. 18 takes us up to -2. So this is based on R, the approximate rate function. This is the approximate accumulation of height. The approximate accumulation of height. Okay, and then for the height above the ground, the height above the ground? So instead of starting at 0 height, what does it start at? 50, and then it accumulates height from 50. So this whole graph, if we wanted the height above the ground, we take this graph and do what? Add 50 to every y coordinate. Move it up, start at 50. Just move that thing up 50, and it would look exactly the same, but just up starting at 50. That'd be the height above the ground. Okay? So, where we're going then is, what do we really want? Is this what we, is this the the actual accumulated height function? No, because it's based on the approximate rate function. It's based on this, and is that approximate rate function any good? It's quite divergent from the actual rate function, right? Because we've got these huge intervals, 2 seconds. So look at this. Near 4 seconds, what does the rate function predict? Should we do this on the screen? Pointing at the screen. So look at near 4 seconds. What does our approximated rate function predict the rate is? -3. What is the actual rate near 4? It's like +8. You see that? So this blue approximate rate function is doing a very poor job, especially at the ends of the intervals, because it's approximating here, say, -3, where it's really like +8. That's not even close. Okay? So, but anyway, it's okay for our purposes now. But where are we going? Where are we going? So we got this approximate accumulation function from the blue approximate rate function. What do we really want? We want to know how much of it you have at every moment. So what would that be like? What would that be like? So we know approximately how much we have at every moment, or in terms of accumulation. So what we want is exact, right? So we want exact. So the exact accumulation function, is it going to be below this, around where this is, or above this? So what is our rate function doing? Is it predicting changes that are too negative or not negative enough? Too negative. So the actual accumulation function we expect would be where? Above, right? So here's what it is. And this is where we're going. This is our goal, is to be able to derive that, okay? Starting with the red curve, we want to get the black curve, right? Given the exact rate of change, we want to get the exact accumulation function. Okay, so there's those four functions we're talking about here in the next couple weeks. Okay? And this is how we're going to use the notation we're going to use. R sub B, little r, A sub B, and capital A. So I want you to tell the person next to you, what is in this journey that we're taking, you know how fast something is changing every moment? You want to know how much of it you have every moment. What would be the order of the process to do that, of these four functions? So put these four functions in order as a process that reflects this statement that we're doing right now. Talk to the person next to you. Is that question clear? Put the four functions in order to reflect that process to answer that question. Go. Yeah. That's the approximate. Approximate based on the approximate rate. But that's maybe worth something. Okay. So okay. This is a couple of questions on the exam. This very question I just asked you. This is a question on the exam. What is the process we've been working on? What's the order of the functions? Okay? So 100%. Everyone's going to get this right. Why? Because this is the very biggest picture of what we're doing. And this should be the first thing we should know. Like, let's have this down so that it doesn't make sense to get to get into any detail in this if you don't have this first foundational idea down. So in this process, you know how fast something is changing at every moment. You want to know how much you have at every moment. Which function comes first? Some are saying R, some are saying R sub B. You know how fast something is changing at every moment. Which function is that? Thank you. Good job. The exact rate of change function. That's that you know how fast something is changing at every moment. Okay, let's go to number 4. You want to know how much of it you have at every moment. Okay, I heard A and A sub B. Which one tells us exactly how much we have at every moment? A sub B, the exact accumulation function. We have the exact rate, we want the exact accumulation. That's the journey. So then the question is, how do we get from R sub B to A sub B? Number 2 is? R. And number 3? A. That's what you did on your quiz, right? So this was your quiz today. That idea was to go from R to A. In your quiz, you went from R to A. Okay, so this is on the test. There are questions. This is the exact question on the test. What is the order of the functions that reflects the process we're working on? You just have to know this. Exact rate of change, approximate rate of change, gives us approximate accumulation, and then we're gonna bridge to exact accumulation. That's so, and don't just write that down because you want to get it right in the test. Have this in mind as we're working on all the details of this. As we're involved in, our heads are buried in the minutia of things. We got to keep track of that. That's what we're doing. Question is okay. Does it make sense? Okay, so you read about over the weekend. You read about the basketball rocket. Let's work on that. Didn't you? A little bit. Beginning of chapter 5 wasn't the basketball rocket? Okay, if I don't know. If you didn't, okay. All right. Okay, so over here on the left is a velocity function with respect to time for a basketball. It's rocket power. So I have some questions. What kind of function is V? Is it rate of change or accumulation? And is it exact or approximate? What are the dependent and independent variables of function V? Talk for 30 seconds. Go. Okay, it's exact rate of change. It's exact rate of change. So the dependent variable is the velocity in meters per second. That's rate of change. And the independent variable is the time elapsed since launch. Okay? So if we wanted to develop an accumulation function associated with V, what are the independent and dependent variables and then the units of those? Okay, so what would the independent variable, what would the dependent variable be? What would the units of each of those variables be for the accumulation function that we want to get from the velocity function? Go. Okay, independent variable would be? What's the independent variable? Same as for the rate of change function. So we're always going to keep our same independent variable throughout this process of getting accumulation from rate. Same independent variable time. Now the dependent variable would be, what would it be? Height, right? Height in meters, right? So meters per second is rate of change. We want the accumulated meters, or height above the ground, as a total amount, okay? I should have said changes in height, okay? So it gives the accumulated changes in height, this should say. Accumulated changes in height. If the rocket is launched from the ground, then the accumulated changes in height and the height as an amount function are the same function because it's starting at 0. Does that make sense? If the rocket starts from the ground at 0, like the ball starts from the ground at 0, the accumulated changes in height and the height above the ground are the exact same function in that case. Okay. So let's stop it quick. Somewhere around here. I went too far. Okay, so I'm going to stop it right there at t equals 5. So I'm going to stop the animation at t equals 5. Express the coordinates of the point. What does the value of v5 represent? And what does the value of v5 mean for values associated with the accumulation function? Okay? Talk. Take a minute. Thanks. You scared me. I thought something was a lot worse than that. Thank you. No further. Okay. That's on 5 now. Sorry. Well, what would you do, I should say? Okay. So I had another question there. What would you do to estimate v of 5? And that's an important question. So take 20 more seconds to answer that. What would you do to estimate v of 5 with the information that you have? Go. What would it be? To estimate v of 5? Okay, here we go. Coordinates. What are the coordinates of that point at when t equals 5? 5 comma v of 5. 5 comma v of 5. And what does the value of v5 represent? What is it? Is it a change? Is it a total amount? Is it a rate of change? It's a rate of change. Go ahead. Okay, at the instant 5 seconds? At the moment 5 seconds, right? We need a little change, right? So it's the rate of change of height of the basketball at the moment 5 seconds. Okay, what do we do to estimate that rate of change? What do we do to estimate that rate of change? I take a little point on this side, and I take a little point on this side, and I do dy over dx, right? It's a rate of change function. It's the value on the y-axis. That's what a rate of change function is. Values of the dependent variable, values on the y-axis, are values of rate of change. So this, you just look for the y coordinate. So this is something that doesn't stick easily for a lot of students. On a rate of change function, the value of the y coordinate of any point is the value of rate of change at that moment, x. So it's about 8 meters per second, about. When do you take 2 points and do dy over dx to get a rate of change? If you have an amount function or an accumulation function, you're looking for a little change, the ratio of the changes, okay? But if you have a rate of change function, it's just the y coordinate. Okay, and what does that number mean, v of 5, or 8 meters per second at the moment, relevant to the accumulation function? We all should know this now. What does that mean, 8 meters per second, or v of 5? Say either way you want. Ada, can you say what it is? What is v of 5? Okay, it's like a little constant rate over the moment, which means okay. All right, so for any change in time in the moment, t equals 5, the change in height would be v of 5 times that change in time. Okay, so the change in height of the rocket is v5 times the corresponding change in time. Now, within the moment. Within a moment at 5. Because if it's not within a small moment at t equals 5, what's happening? The rate is changing. As soon as you move away from t equals 5, you have a different rate. So we have to use that as a constant rate. We have to say only in the small little moment around t equals 5 can we assume a constant rate right there. Okay. Questions on this warm-up stuff? Okay. Yes, please.
Sometimes causes the confusion, like for the first one.
Yeah.
So since that's the coordinates for rate of change function.
Yeah.
Shouldn't that be 5 comma r sub v of 5?
I think on the previous screen I just called it v. I just said the name of the function is v. Yeah. So from the other examples, it would have been r sub v. Yeah. Right. So if you're going off what we did like with the oil slick and then this r sub b, it would have been r sub v. Yep. Exactly. And then when I started this example, I just called it v. So it's equivalent to this v function is equivalent to like r sub b that we had in the quiz. Yep. Okay. Good point. Other questions? All right. And then here's that mathematical result of having that rate of change. For any little change in time, change in height is that rate times the change in time. Okay, so we are going to approximate the height of the rocket at t equals 5 seconds. All right? Using a delta t of 0.9 and the rate of change at the beginning of each. So here is then our R function. I drew it for you because we know what that's about. What that's an approximate rate function. We cherry pick rates, right? We cherry pick rates from the beginning of every interval from the actual rate function, and we make constant rates. And I'm using delta t of 0.9. And so what interval are we in then here at t equals 5? Well, so there's 0.9, then 1.8, 2.7, 3.6, 4.5. So how many was that? 0.9, 1, 2, 3, 4. So there's what we call here 5 completed intervals. This is important terminology. When we get to t equals 5, in terms of our approximate rate function, we've made it through 5 completed intervals. And now this interval then is called, because it has the current value of t in it, t equals 5, it's called the current interval. Really important terminology here. So when t equals 5 and delta t is 0.9, time has elapsed through 5 completed intervals, and at t equals 5, the 6th interval is what we're going to call the current interval, because that's where t equals 5 lies. Does that make sense? So how are we going to get the total accumulated change? What's going to be the strategy for that? Well, so we're going to consider all the changes in height accumulated within the completed delta t intervals, 5 of them, and then a little bit more change that we get in part of the current interval, right? Because we don't make it all the way through the current interval. So this is going to be a really important thing for us. So the total accumulated change is going to be the total accumulation through the completed intervals plus a little bit more accumulation in the current interval. All right, so what is the total accumulation in the completed intervals? How much accumulation do we get in the first interval? Can we write it symbolically? So in the first interval, how much accumulation do we get? So you have to, yeah. How would you write, so here, it's actually there, it's on the axis. How would you write it symbolically? So how would you calculate, write it symbolically to represent how much accumulation you get in the first interval? Anyone should be able to do that. We need DH. We're asking for a little change in height for this first interval. And the 0 comes from what? 0 is what? Okay, symbolically, V of 0, the left side, right? The rate at the left side. Changes in height are the rate times changes in time. The rate times, what's the change in time? Delta t. M dt, or M dx, right? M dx, rate times the change, that's for the first interval. Second interval. What would it be? We want the rate at the left side of the second interval now. So that's the amount of change from the first interval. M dx. Or in this case, the rate times delta t. So we're going to do that again for the second, and then the third, second, third, fourth, fifth. 2, 3, 4, 5. And then we want to get that amount. All right, you do it. Write amount. Constant rate of change. Constant rate of change. Summing, so we're just going to, for each interval, we want the total amount of change in each interval. Using the approximate rate function, the horizontal lines. Always using the value of t at the left side of the interval to get the rate. And that rate is going to be the constant rate for the whole interval. That's what we're showing with those horizontal lines, and that's why we can calculate these constant rate of change, because we're assuming that is the constant rate for the whole interval. It's not actually, right? The red curve is the actual rate. We're using this constant rate step function in order to be able to calculate some changes, right? Last one. Okay, so now, I'm not going to write out all the math, but this function is t to the 1/3. Okay, that's what this actual rate function is. So we can use t to the 1/3 to get these constant rates, to get actual numerical values, okay? Make sense? So for instance, what's v of 2.7? How would you get that rate of change, v of 2.7? How would you get that value, actually? 2.7 to the 1.3, right? That's what this function says. At 2.7, take 2.7 to the 1.3, it gives you that rate of change, which is equivalent to what you might estimate on the y-axis, right? The rate of change on the y-axis. Okay, when you do all that, you get, I'm not going to write it all out, you get 10.75 meters. So that's the total accumulated change from the completed intervals before t equals 5. That's the total accumulated change due to the completed delta t intervals before t equals 5. 10.75 meters of accumulated height change. So at home, if you do it, so find all those values. Each delta t is 0.9. Add them all up. Okay, what about the current delta t interval? How are we going to get, there's a little more change for the current interval. Any questions about what I did? Number 1, completed delta t intervals. Yeah? It's the total accumulated change from the completed intervals. Right? So we've got 5 completed intervals. We're interested in t equals 5. That lies right in the middle of one of these intervals. Do you see that? So to get the total accumulated change up to t equals 5, there are completed intervals that stop at 4.5, and then there's a little more change due to something less than a completed interval. So this is just the change due to the completed intervals, right? 5. So mdx plus mdx plus mdx plus mdx plus mdx for each interval. Is it better? Okay. All right, how are we going to get a little amount of change in the current interval? Question?
Yeah, how'd you get t to the 1.3?
I gave it, I'm telling you that's what it is. That's the original, get it. That is the function, the actual rate function, the curve. And then you could use that to get the values of these constant rates. V sub 0, 0.9, that we're using for the constant rates for our approximate rate function. Other questions? Okay. So where are we at? That interval ended at 4.5. We're all the way here at t equals 5. So can you figure out how much change now there is due to the current, that? You should be able to do this if you're tracking. How much change, find a number, how much change is there, what accumulated amount of change just in the current delta t interval? Can you figure it out? Go, do it. Okay, so we want to get this amount of change from just the partial current. In the current interval, we have a partial, we elapse through a partial interval. We want to get a little bit of accumulation from that. It's not hard if you're tracking what we're doing. Yeah. So what is the rate in this current interval? How do we define the rate? What is it? V of 4.5. right? It's just, it follows from all, it's the, based on how we're making an approximate rate function, it's the rate at the left side of the interval. So v of 4.5, okay, good. Times 0.5. Instead of 0.9, we don't make it all the way through, right? How far do we make it? 0.5. And did anyone do that? 4.5 to the 1.3? I agree. So this last partial interval was a little accumulation of 3.53 meters. Therefore, what's the total accumulated change in the first 5 seconds? How would you do it? What would you do? Just add them, right? You have the accumulation from the first, all the first completed intervals, and then plus the little accumulation from this partial interval, and 14.28 is what I think you should get. And then, lo and behold here, look. That's what the height, that's what this is showing right here, 14.28. So, and this is showing here that accumulation, right? So this is showing the accumulation from the completed intervals. And then this is this last one here is that 3.53 from the partial interval right there. So it's just stacking them up. The total is 14.28 meters of total accumulated change from the 5 completed intervals and from the partial interval. So this is an important principle here. I saw your hand first.
For the current interval,
yeah.
Other than being named different than a completed interval, yeah. Is it also always literally going to be less than a completed interval?
Yeah, because if you're in the current interval, then you haven't completed it. So that amount of the amount of change in your independent variable is less than delta t. And in fact, this 0.5, I'm glad you mentioned that. This 0.5 right here, we have a name for that. It's how much we've changed in the current moment. How much we've changed in the current moment. What is that? Yeah. Almost. No x's here. Yeah, you got it. Yeah, you got it. dt. That's dt. So we have the completed intervals, and then the current interval, dt is going to vary through the current interval. So right now, at t equals 5, dt is 0.5. Delta t is a parameter. It doesn't change. It's a constant value, 0.9 every interval. But then in the current interval, dt will vary from what to what? dt will start at 0 and vary to 0.9, and then you're in the next interval, and it does it again, 0 to 0.9. Next interval, 0 to 0.9. Right now, at t equals 5, that dt value is 0.5. Yeah, so do you see these little tick marks here? That's showing, yeah, so all of this is our 10.75 right there, showing the accumulated little amounts from the completed intervals, and each tick mark is showing each one of these. And then this last one is our 3.53 right there for the partial interval. And so the total accumulated height then is the 14.28, which is, that looks pretty accurate right there on the scale, 14.28. Other questions? Okay, but so what do we really want? So this was just for t equals 5. What do we want to know? We want to know the accumulated height of the basketball, what, at every moment. So that was a lot of work to do just for one. We just looked at one moment, t equals 5, to get the accumulated. That was a lot of work. Our goal is to generalize this so we have a function that will give us this accumulated amount at any moment. That's a function. That's a function. So we got to start bridging towards that. Questions before I erase this? Keep walking around. I see more even. So I've been. Here's how calculus is going today. poker, drawing in paint, music, games, English essay, what was it? Clean? Chemistry homework, Facebook and Apple Messenger, reading another text, looking at a map, and watching videos. So this is in calculus, you guys. And so this is a really, really hard class. Lots of you are struggling. And my suspicion is that these aren't the people who are getting an A in the class right now. Okay? Okay. So you got to be tuned in and taking really good notes. Okay? So just want to encourage you. This now it's going to get hard. If you think it's been hard up to now, now it's when it really gets hard because we're going to start building, like I said, a function that gives us the accumulated height at any moment. This is hard stuff, okay? So please stay tuned in. We're going to probably talk about what kind of consequences would amount for this kind of stuff. I mean, if we have to police you to pay attention, we will do it. That's how important it is, okay? But hopefully you have the motivation here. Okay, so that's our pep talk. So what do we say? We need a function now. So we want to get the basketball rocket at any time t. So let's bring it back to 5 here. So this is the current. This is going to be the current interval, and that current interval is starting at what? The current interval starts at 4.5. Can I fit it in there? I cannot. I'm doing the next screen. There's a bigger one. There we go. Okay. The current interval starts at 4.5. And then we have what? Now, so this is for the that blue is a little part of the accumulation function in the current interval. So the current interval has a width of delta t. Can I get some water? I'm about to die. All right, so this is the current interval. It has a width of delta t. And so what do we say? In the current interval, dt is going to vary through the current interval. And so as it does, we want to get a record of every correspondence point and build that function, right? So so dt, imagine dt varying through this interval and generating all the correspondence points through the current interval. So our current interval is the 6th interval. It starts at 4.5, h of 4.5, right? And so then this is our generic anytime t, but this in particular will be between, what, 4.5 and 5.4. So we're going to write the function for when t is between 4.5 and 5.4. Okay? And what does that mean? That means writing what this thing equals. Okay? And we have you have the tools to do it. It's just, do you remember and can you apply it? Okay? And so it might take an intermediate step. So we have what? We have a starting amount of height, and we want to get a final amount of height. Okay? Generically for any t based on a dt in the current interval. Okay, I want you to work on that. So you have to apply it to these principles that we've been doing over and over again. We got constant rate of change. So can you apply the principles of constant rate of change to find that value h of t, which is a generic amount of height for any point, correspondence point in this current interval? So this is, just to let you know, this process to do this is a repeat of what we've done the last month. It's a repeat of what we've been doing the last month. See if you can try to remember and latch on and apply what we've been doing. No, you don't need that. You don't need that. But yes, yes. Here's a hint. There's your hint. Okay, so how do we do? Can anyone get me started here? So h of t equals, yeah.
H of t equals h of 4.5 plus v of 4.5 times t minus 4.5.
Well done. We're going to take it one step at a time. So essentially, yeah, excellent. So essentially, but to get started, h of 4.5 plus what in a nutshell? What's all that other stuff you said in a nutshell? dh. So what? Final value of the height equals initial value of the height plus, how many people just got that much? If you got that much, at least half maybe? Okay, I think about half. Okay, good. So, but this is what, we want h as a function of t. So we got to rewrite dh. How can we rewrite dh? Okay, so that's a change in height, and we got constant rate of change. How can we rewrite dh? In the back, I see you.
Would it be t minus 4.5?
Okay? I think that's dt, but we're going to need that. That's good. Excellent. So dt is t minus 4.5, right? Final time, which is the time t, minus 4.5. So that's good. So what about dh? Somebody new, yep.
H of t minus h of 4.5.
Yeah, but we can't write, we're trying to write a definition for h of t. So we don't want to use final minus initial again, because then it just everything cancels out. We got 0 equals 0. So we don't want to use that. We want to use constant rate of change. Constant rate of change to do this. Yeah. Okay. Okay, m times dt, right? So this is our constant rate of change. dh equals mdt. So the question is, how do we represent, or what is m? What is m? Yeah. Wow, our pep talk worked. All of a sudden, brains are on. All right. V of 4.5 times dt. Okay, so dH is the constant rate times the change in time, and that constant rate, what? It's the constant rate at the start of the interval, V of 4.5. And so then she said, what is dt? So last thing here. H of 4.5 plus V of 4.5 times, we want it truly as a function of t. That's the t minus 4.5. So that is a little piece of the accumulation function. It's the piece that works, it only works in this interval. When t is between 4.5 and 5.4, and that sixth moment, the sixth delta t moment, this would give us the height, the accumulated height, starting at 4.5 seconds, ending at 5.4 seconds. You plug in any t value, and that would crank out the associated height. Okay, so we're getting closer. So this is just a little piece of an accumulation function. We could write that. We could have written this for every individual. So hold on a second. Hold on a second. So with what we've got so far, if we wanted to get the whole function, we'd have to write this something like this for each individual interval. We'd have this something like this for the first interval, and then something like this for the next interval. And you're always taking the accumulated height from the end of all the previous intervals, plus the little amount of change for the partial interval here. Okay, question?
Okay, so V is basically the rate of change. You just, instead of putting R of a function, you just labeled it V instead?
Yeah, so
okay,
it's like we did R of V on the quiz. So if I were consistent, instead of V, I could have used R of V. It's that exact rate function that we start with. And it was the one that I did all the setup work.
Right. I was just starting off by V, and then I thought that it was...
Yeah, so this is our exact rate function. And when we take it just at the left side, we make it the constant rate for that whole interval.
Okay, so if you were to write it the other way, it would be R sub V of 4.5.
If I would have defined the function from the beginning as R sub V.
Okay.
But I defined it as V. But that's the same thing.
Right.
Okay, cool. Other questions? Okay. Have a good weekend. Study. Yeah.
Get the equation for all of them, but in this case, if it starts at 0, just plug in 0 there, and in this case, that would make that t, and then t times dt plus whatever the starting
0.
That would have to be v of 0 to get all
So in the first one, we don't have any accumulated height. We should write h of 0 over just nothing. We don't have so it would just be the constant rate for the first interval times dt. How much we go in the first interval. Then we get an accumulated amount of height. We go into the second one. Take that accumulated amount of height, and we add on the little accumulation we get through that one.
Right. So to get the function for all of them, it wouldn't be vt. It would be v of 0.
No, you have to get for all of them. We have to have a line like this for every interval. That's what I'm saying. Every interval would need its own line like this. It'd be a piecewise function. So you can't just throw in a t and then say it's everything. No, because in every interval you have a different constant rate. Right? Each interval has its own constant rate. So we need a new line with a different constant rate for each one.
I want to ask about the delta t. I got really confused about delta t. Whenever you put like each interval change, is delta t the same as t equals 5 or?
No, delta t is the width of the moment. It's the width of the moment. We said it was 0.9. It doesn't change. It's
based on that graph, right?
Yeah, so I'll just start. Our intervals are 0.9 wide. That's delta t. 0.9 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 delta t. That's why we always multiply by the same delta t. We decided, let's say, slide equals height equals 5. Okay? And so then you get to here, so this is 0.9, but then this is not 1 that's less, 0.5. Imagine, see, comparing that positive equals 5. And that was the problem we worked out. Then we said, let's get all values of t through that. And that's what this does. This now gets us accumulated height for all values of t through that 6th interval. So you plug in your t and it tells you the height. Is that a little better? But yet delta t is 0.9. That's set. That's 0.9.
Actually, that's over here because I have a hard time seeing things over that side. Thank you.
Okay, thank you.